So far, we have discussed about two scheduling algorithms, which are the first come, first serve scheduling and the shortest job first scheduling. So moving on, in this lecture, we will be studying about the next scheduling algorithm, which is the priority scheduling. So in the previous two scheduling algorithms, we have seen their properties, we have seen how they work, and we have also seen their advantages and disadvantages. So in this lecture, we will be seeing how this priority scheduling works, and we will be seeing if this is a good algorithm, what are its advantages, and if it has any disadvantages, and how it can be solved. Alright, so let's get started. So in this priority scheduling, what happens is that a priority is associated with each process and the CPU is allocated to the process with the highest priority. So from the name itself, we can try to understand that in priority scheduling, what happens is that each process is having a particular priority. And based on their priority, the scheduling will take place. So the process that has the highest priority will be given the CPU first. And then the process which has the next priority will be given the CPU next, and so on. And if we have two or more processes with equal priority, then they will be scheduled in the FCFS order, which is the first come first serve scheduling order. So if there are two or more processes having the same priority, then the process that arrived first among them will be given the CPU first. So that is how priority scheduling takes place. So in the previous lecture, we have studied about the shortest job first scheduling, and here we can define the shortest job first scheduling in terms of priority scheduling like this. An SFJ algorithm is simply a priority algorithm where the priority is the inverse of the predicted next CPU burst. The larger the CPU burst, the lower the priority, and vice versa. So the shortest job first scheduling is also basically just a priority scheduling where the priority is determined by the next CPU burst. So we have seen that in the shortest job first scheduling, the process with the smallest next CPU burst will be the first to get the CPU. So we can say that the next CPU burst or the predicted next CPU burst is the factor that determines the priority of this scheduling algorithm. So what we mean by this sentence, where priority is the inverse of the predicted next CPU burst. Why we say this is because the larger the CPU burst, when the CPU burst is large, then the priority is low. Because a process having the shortest CPU burst will be the first one to get the CPU. So that process will be of higher priority. So the larger the CPU burst, the lower the priority. The smaller the CPU burst, the higher the priority. So that is what we mean by this sentence here, where the priority is the inverse of the predicted next CPU burst. So SFJ algorithm also is simply a priority algorithm with this factor. So this priority scheduling can either be preemptive or non-preemptive. So we have talked a lot about preemptive and non-preemptive schedulings, and we know what it means. So priority scheduling can either be preemptive or non-preemptive. So let's see what it happens when it is preemptive and when it is non-preemptive. So what happens in a preemptive priority scheduling is that a preemptive priority scheduling algorithm will preempt the CPU if the priority of the newly arrived process is higher than the priority of the currently running process. So what happens is that if we are following a preemptive priority scheduling, then if the newly arrived process has a higher priority as compared to the process that is currently executing in the CPU, then the CPU will be taken away from that currently executing process and be given to the newly arrived process with higher priority. So that is what we mean by preemptive priority scheduling, and that is what happens in that. Now, what about non-preemptive priority scheduling? So in non-preemptive priority scheduling, what happens is a non-preemptive priority scheduling algorithm will simply put the new process at the head of the ready queue. So if we are following a non-preemptive priority scheduling, then if a new process arrives with higher priority than the one which is currently executing, even then the currently executing or running process will not be disturbed, but the newly arrived process will be just kept at the head of the ready queue. That means it will just be kept in the queue according to its priority. So if it is having the highest priority among all the processes in the queue, then it will be kept at the head of the queue. And then when the currently executing process completes its execution, then the newly arrived process will be given the CPU for its execution after that. So that is what happens in a non-preemptive priority scheduling. Alright, now let's take some examples to understand this in a better way. So here we have an example. Consider the following set of processes assumed to have arrived at time 0 in the order P1, P2, P3, P4, P5 with the length of the CPU burst given in milliseconds. So here we have a table with processes with process IDs P1 to P5, and here we are given their burst times, and here we are given the priority. So it says that they have arrived at time 0 in this order P1, P2, P3, P4, P5. And burst time is the time that a process will take for its execution. And here we are given the priority. So this is a priority scheduling. So with each process, there is a priority associated with it. So in some books, you will see that the higher the number or the value here, the higher will be the priority. And in some books, it may follow a different way where the lower the value, the higher the priority. So we will be following the second method where the lower the value, the higher the priority. That means here 1 will be the highest priority, 2 will be the next, 3 will be the next, and 4 after that, and 5 will be the least priority. So smaller the value here, the higher is the priority. So keep that in mind as we proceed with this example. Alright, so what we are going to do now is we will form the Gantt chart for this if these processes arrive in this order and if they have this burst times and if they are having this set of priorities. Alright, so let's see how we can form the Gantt chart for this. So using priority scheduling, we would schedule these processes according to the following Gantt chart. Alright, so let's see how we form this Gantt chart. So if we look at these processes, which is the process having the highest priority? So as I already told you, the smaller the value, the higher is a priority. So here process P2 has a priority of 1. So that means P2 is the one with the highest priority in this list that we have. So P2 will be the process to first get the CPU. So P2 gets the CPU over here. And how long will P2 execute? P2 will execute for 1 millisecond because that is the burst time of P2. So P2 executes from 0 to 1 milliseconds. Now, which is the next process that will get the CPU? So here we assume that they have all arrived at time 0. So they are all there present in the ready queue. So after P2 completes its execution, which is the process having the next highest priority? It is P5 with priority 2. So P5 will be the next one to get the CPU. So P5 will get the CPU after P2 completes its execution. And how long will P5 execute? It will execute for 5 milliseconds. So from 1 to 6 milliseconds, 1 plus 5 is 6. So up to the 6th millisecond, P5 takes the CPU and does its execution. Now after P5, what is the next process having the highest priority? It is P1. P1 has a priority of 3, which comes just after this priority 2. So P1 will be the next one to get the CPU after P5. And how long will it execute? It will execute for 10 milliseconds. So at the 6th millisecond, when P5 releases the CPU, P1 gets the CPU and executes for 10 milliseconds. So 6 plus 10 is 16. So up to the 16th millisecond, P1 executes. And after that, who will get the CPU? Let's see. P1's priority was 3. So what is the next highest priority after P1's priority of 3? It is P3 with a priority of 4. So P3 will now get the CPU and execute for 2 milliseconds. So 16 plus 2 is 18. So up to the 18th millisecond, P3 uses the CPU. And then after that, which is the next one to get the CPU, it is P4 with a priority of 5, and it is the last process. So P4 gets the CPU after P3 releases it at the 18th millisecond, and it executes for a burst time of 1 millisecond. So P4 executes from 18 to the 19th millisecond, and here it releases the CPU. So this is the Gantt chart for this priority scheduling when we have these processes that have arrived at time 0 and they have this set of priorities and this set of burst times. Alright, so now let's try to calculate the waiting time for this set of processes. So calculating the waiting times are very easy. We can just look at this Gantt chart and just write the waiting times here. Waiting time for P1, where is P1? P1 got the CPU at the 6th millisecond. So the waiting time for P1 was 6 milliseconds. So let's keep in mind that they have all arrived at time 0. So that is why we can just simply look at when they got the CPU in this Gantt chart and write the waiting times for this particular example. So what is the waiting time for P2 next? P2 was the first one to get the CPU, so the waiting time of P2 is 0 milliseconds. And for P3, what is the waiting time? P3 got the CPU at the 16th millisecond, so the waiting time of P3 is 16 milliseconds. And for P4, it is 18 milliseconds similarly. And for P5, what is the waiting time? We see that P5 got it at the first millisecond. So the waiting time for P5 is 1 millisecond. So what is the total and average waiting time for this? So the average waiting time will be 6 plus 0 plus 16 plus 18 plus 1 divided by the number of processes, which is 5, which gives us 41 divided by 5, which is 8.2 milliseconds. So the average waiting time for this set of processes when they follow a priority scheduling is 8.2 milliseconds. Alright, so now we have seen how this priority scheduling works. Now we have seen that so far it is very good, but is there any problem that we have with this priority scheduling? So can you guess about any problems that could occur if we follow this priority scheduling? So here is a problem that we have with this priority scheduling. So a major problem with priority scheduling is indefinite blocking or starvation. So what do we mean by indefinite blocking or starvation? Let's see. A process that is ready to run but waiting for the CPU can be considered blocked. So when a process is waiting and is ready to be run but has not yet got the CPU is considered as a blocked process. Now, a priority scheduling algorithm can leave some low priority processes waiting indefinitely. So this is the problem that we have. So there are processes waiting in the ready queue, ready to be executed and waiting for a CPU. But if there are some low priority processes that are waiting in the queue, and there are many other processes with higher priority as compared to this low priority process, then what will happen? This process of low priority will get the CPU very late, or in a worst case, it may even never get the CPU, because let's say that there is a low priority process and then all the processes that arrive are having higher priority as compared to this low priority process. Then what will happen? All the higher priority processes will be getting the CPU, and this low priority process, since its priority is lesser as compared to those other high priority processes, it will never get the CPU. So in a heavily loaded computer system, a steady stream of high priority processes can prevent a low priority process from ever getting the CPU. So that is what I just explained. So in that case, the low priority process will be indefinitely blocked, or we also call it starvation. That means it is waiting to get the CPU, but it's never getting the CPU. It is starved from the CPU. So that is what we mean by indefinite blocking or starvation. So that is one problem which we have with this priority scheduling. So now what is the solution to this? Can you think of any solution that we can come up with in order to solve this problem of indefinite blocking or starvation? So here is a solution to that problem. A solution to the problem of indefinite blockage of low priority process is aging. So what do we mean by aging? Aging is something that we are going to use to solve this problem of indefinite blockage or starvation. So what is aging? Aging is a technique of gradually increasing the priority of processes that wait in the system for a long time. So what we mean by this is that when a process is waiting for the CPU in the system for a long time, then it ages. It will undergo aging. So when it undergo aging, what will happen is that we will increase the priority of the process as it ages. So if the process is waiting in the queue for a long time, so by the means of aging, we will increase the priority of that process gradually. So when a process is waiting in the ready queue for a long time, gradually by the means of aging, we will increase its priority. So when a process is waiting for a long time, slowly its priority also gets increased. And hence a time will come when its priority is also greater than some of the other high priority processes that have arrived, and hence that process will also get the CPU for its execution. So it will not remain there being indefinitely blocked or starving for the CPU. So the priority of that process gradually increases. So that is a good solution that we have to this problem of indefinite blockage or starvation. So let's take an example. If priorities range from 127, which is the lowest priority, to 0, which is the highest priority, we could increase the priority of a waiting process by 1 every 15 minutes. So if we are having this range of priorities where 0 is the highest priority and 127 is the lowest priority, then we can increase the priority of the waiting process by 1 every 15 minutes. So let's say that there is a process with a very low priority, let's say the lowest priority of 127, and it is waiting, and there are many high priority processes coming and using the CPU, and this process is just waiting and waiting and waiting. So what do? After every 15 minutes, we are going to increase its priority. So in this case, increasing means this value have to decrease. 127 will become 126, and after the next 15 minutes, it will become 125, and after the next 15 minutes, it becomes 124, and so on. So after every 15 minutes, we are increasing the priority by 1. So what will happen? Eventually, even a process with an initial priority of 127 would have the highest priority in the system and would be executed. So even if all the processes arriving after that particular process is always of higher priority, even this low priority process, after a particular amount of time, its priority gets increased and increased and increased, and a time will come when that process will also be of highest priority, and hence it has to get the CPU for its execution. So we make sure that that process will get the CPU for its execution and it does not undergo indefinite blocking or starvation. So this is a good solution that we have to this problem. That is, by the process of aging, we are going to increase the priority of the processes as they wait in the ready queue. So that is the solution to the problem that we have in this priority scheduling. So I hope you're clear with that. That is how priority scheduling works, and that was the problem that we had, and this is how we solved the problem. So in the coming lectures, we'll be discussing some problems on this priority scheduling. So I hope this was clear to you. Thank you for watching and see you in the next one.